In this lecture, I'll be introducing the word buffer and the Henderson-Hasselbalch equation in order to help us understand when we have a buffer, when a question with acid and base equilibrium sets us up for a buffer, and how we can answer it using ice tables, equilibrium tables, and or stoichiometry tables. So acid-base equilibrium gets a little bit confusing. There's so many moving parts because sometimes you're going to have complete stoichiometry, which I like to call titration, and then sometimes you're going to have equilibrium problems, and it gets all messy sometimes. So let me show you a classic acid-base problem. This is one that's been released by the AP Central for a while, no big deal. And I'm going to show you where we have a titration, which would give us a stoichiometric part of the problem. And then I'll show you a part where it's an equilibrium problem, and we'll solve it using ice tables, and then we'll solve it using another equation. And again, this is going to make more sense if we see how titrations work in terms of titration curves. So let's get started with the application of where all this messiness happens. Okay, first and foremost, I have a problem where I have a weak acid. And this weak acid is being reacted with a strong base. Here's my strong base. Now, my strong base is going to pull the H's off this weak acid stoichiometrically. What I mean by that is, for as many hydroxides I have, that's how many H's will come off the HF. Now, HF, okay, has a Ka that's very small. I believe it's 7 point, let's see, I have it written down here somewhere. It's 7.2 times 10 to the negative 4. It's got a very small Ka. What does that mean? Well, equilibrium constants means it's the concentration of the products over the concentration of the reactants. And that equals our equilibrium constant to some stoichiometric coefficient. But the bottom line is, if the K is small, that must mean there's a lot more reactants. If there's a lot more reactants, that means that this guy does not like to dissociate. However, in this problem, I put a strong base here, and strong bases will yank this proton away to create the water, whether HF likes it or not. So when I say you have a stoichiometric problem, I'm also going to say we have a titration. You have to recognize when you have a strong acid and a strong base, they're going to react stoichiometrically. If you've got a strong base and a weak acid, as in this case, they'll do the same, because the strong base will make the acid act as if it's a strong acid and make it completely dissociate. Only when the acid, like HF, is surrounded by something like water will it only come off and go forward a little bit. But if I've got a base, a strong base in its way, it'll force its hand. Now also, the opposite is also true. What I mean by that is I could have a weak base and a strong acid, and the strong acid will force the weak base, okay, to accept a proton in this case. But in any case, we're forcing the hand. So this is a titration. And so this part of the problem, and this is a problem where I take hydrofluoric acid and I titrate it with a hydroxide. And I'm giving you maybe a molarity, and I'm giving you some volume. And from that, I figured out the moles of HF and the moles of hydroxide. So given some molarity and some volume, I figured out the moles. Why? How do I do that? Well, molarity is moles over liters. So if I know the volume in liters, if it's in milliliters, I can convert it. And if I know the molarity, I can figure out the moles. Now, why do I care about moles? Usually these tables are based on molarity. Well, this is a titration problem. This is where this hydroxide is going to annihilate as many HFs as it can. So for as many hydroxides they are, that's how many HFs are going to dissociate. It's going to force it to happen. So because I have 0.006 moles of hydroxide, and I have 0.01 moles in my problem that I'm creating or using, I can see the limiting reagent is going to be the hydroxide. Hydroxide is going to run out first because it's a lower number of moles. It's a 1-to-1 ratio. And what happens is we start out with 0.01 moles, we start out with 0.06 moles, and we have 0 fluoride ions. And even though this is not a true equilibrium table, we can still use it. This is the what? Initial conditions. The change is we're going to lose 0.006, right? 0.006 is going to go completely to water as it pulls as many HFs as possible. Well, it pulls 0.06 moles of HFs away because that's exactly how many there is. Now, of course, it goes to 0 because we're going to minus 0.06. That's why it's the limiting reagent. But more importantly, you're going to pull 0.006 moles of HF, and you're going to convert that to the fluoride ion. Notice this is minus X, plus X in terms of moles, in terms of stoichiometry. Don't lose sight of that. So we're going to drive the reaction. This is not equilibrium. We're driving the reaction forward until we run out of what? The hydroxide. So we're driving this reaction. So this part of the problem is a titration. We're going to force the hand of the weak acid by the strong base and drive it as far as we can. Now, obviously, we didn't drive off all the HF because we didn't have enough hydroxide to do so. But this is what happens when we create a buffer. See, it's a partial titration. If I wanted to titrate HF like you've done in previous maybe courses to figure out its concentration, we would have to add exactly the moles of hydroxide to match the 0.01. We're not trying to find the concentration. In this problem, what they're doing is they're partial titrations. So we're taking away some of the HF. Look what we got here. When we pull off some of the HF into fluoride ions, we're left with 0.004 moles of HF, and we're left with 0.00 moles of fluoride ions. Look at that. We have a conjugate acid-base pair that is very similar in the amount of moles. My friends in chemistry, this is a buffer. What is a buffer? A buffer is a solution that has an acid and its conjugate base. So what we have, party people, is we have HF, which is an acid, and we have fluoride ions in solution, which is a base. Now, some people think that these guys would react with each other, but they don't, because conjugate acid-base pairs are related by Ka times Kb equals Kw. Now, Kw we know is 1 times 10 to the negative 14. If the Ka is high, the ability to give off protons, then the ability to accept protons is low. It's an inverse relationship. So as strong as the acid is, the base has to be weaker inversely or as much to equal the same number. So these guys do not react with each other. Why is it a buffer? Well, if I was to add some acid into this solution, okay, well, the solution would prevent the pH of the solution from changing a lot because the base part, F negative, is a base because it can accept a proton and reform the acid. So the acid will be consumed by this base, all right, and the pH would stay very constant. If I was to add some base to this solution of HF and F negative, then this acid part could neutralize it and keep the what? The pH constant. So a buffer prevents a pH swing because it has both an acid that can neutralize any base that's added, and it has a base part that can neutralize any acid that's added, and this prevents the pH from changing much. Now, as long as you don't add too much, because if your acid eats up all the conjugate base, or the base eats up all the conjugate acid, you'll have a huge pH swing. So a buffered solution is one where you have acid and base conjugate pairs. So the best way we can do this to create a buffered solution is to, my friends in chemistry, halfway titrate something. There's other ways, but this is one way we do it. So we've created a buffer. And you may say, why do I care? Well, because there's a way to handle buffers, and we'll get there in a second. So let's look at the rest of this problem. So in this problem, we figured out how much moles of HF would be left. We found out how much F negative would be left. Now, we annihilated the OH, but there's still some HF left. Now, what I did is I converted the moles into a what? Into a molarity. So the moles of my HF went to a molarity. I did this as well for my F ion. So I converted my HF values into a molarity. I did the same for the F negative. Now, why did I do that? Because I know an equilibrium problem is looming. You say, well, how do I know? I've just done a titration, which was pure stoichiometry. This is a no equilibrium zone because this was a completion reaction. We forced it forward. But now what's left over? What's left over is we have hydrofluoric acid and we have some conjugate base. We've got that buffer solution. All right, well, big deal. Well, yeah, it's a big deal because what chemical is in the largest quantity after I drive off the oxygen? Drive off the hydroxide. After the hydroxide's driven off, we're in an aqueous environment. Don't we have a lot of water? And guess what? We're going to have some acid, we have some water, and we have some conjugate base. And we have theoretically no new H3O pluses. So what's going to happen is this is going to go forward a tiny bit. Why? Well, there's a zero here. So we've got to fill that void. So we're going to go forward. Now, we don't go forward a lot because the Ka is tiny. This is a weak acid. Water is not a strong base, so this is not a completion reaction. We have an equilibrium table now. Now we have to consider the Ka. This is not a completion. This is not a titration. The titration's over. We added a little bit of base, drove the reaction. We produced some conjugate base, and now we have some HF hanging around, and we have some conjugate base as a buffer. What's the pH of this solution? What's the pH of this buffered solution? Well, I can do it this way. I know that we're going to go forward a little bit, but not much. So minus X plus X plus X. I'm starting with 0.1 molar. Notice I'm in a molarity. When we do equilibrium, it's a good habit to be in a molarity because at some point we have to fill these brackets, and these brackets represent concentration, molarity. So I do my equilibrium problem, minus X plus X plus X. These are not moles, and I'm minusing X, right? X plus 0 is X, and then 0.15 plus X is 0.15 plus X. Now, if you notice I approximate this away. Because the Ka is so small, I don't go forward much. So the size of this X is insignificant to the size of this number. Same thing here. So I can actually just get rid of these X's. Yes, it's going to go down, but compared to the size of this number, it's not going to go down significantly. And it only works when your forward K, in this case the Ka, is tiny. All right? And you can check that approximation if you solve for X and you compare it to this value if it's lower than 5%. Anyway, getting back to the problem, the Ka is 7.2 times 10 to the negative 4. It's equal to the what? Products over the reactants. Notice I didn't put the water in my equilibrium expression because solids and liquids don't apply. Solids and pure liquids don't have a molarity. So I put them in. I approximated away these X's. Now it's X for the what? H3O plus, 0.15 for the F. HF is 0.1 because I approximated away. And now I'm going to solve for X. This equals this. So when I solve for X, I get 4.18 times 10 negative 4. That's the concentration of my X, which has to be what? My H3O plus here. Now, negative log of that concentration gives me my pH. So the pH of this buffered solution is 3.3. And because it's buffered, it's not going to change much. And that's how we do this problem. Wherein I what? Add some base to drive the acid forward. I've created some conjugate base because I didn't add enough to drive it all the way forward. And now I have what? Both acid and conjugate base there. Now I want the pH of my resulting buffered solution. I now do an equilibrium problem. But you know what? There's an easier way. There's an easier way. And it begins with this derivation. Watch. Okay, we know we had HF plus water breaking apart into H3O plus and F negative. That's the reaction with water. And I'm going to use the one that's in equilibrium. The one with the base is not equilibrium because it drove the reaction one way. It's not equilibrium. It forced the hand of HF. So now, what's the Ka? Just stay with me. The Ka is equal to the what? Remember, this is a liquid. So it's the products H3O plus times the F negative conjugate base over the HF, the conjugate acid. We leave out the water because it's a liquid. Okay, let's solve for the H3O plus because the question that I asked you, what is the pH of the buffer? So when I solve for H3O plus, F goes to the bottom, H to the top. So what I get is Ka times, all right, HF. That's the concentration of my conjugate acid over the concentration of my conjugate base, all equals H3O plus. Now let's rewrite this. H3O plus equals Ka times concentration of HF. Just going to make this nice and pretty. F negative. Okay, all I did. So this is what we have here. Now it should be the concentration of H3O plus. Okay, so what I'm going to do is now try to get pH out of this. Well, I know to get pH of H3O plus, I do the negative log. In fact, if it's an equation, couldn't I do a negative log of both sides? So I'll do the negative log of the Ka and the negative log of this relationship. Do the negative log of everything. That way it's equal on both sides. Well, the negative log of the H3O plus concentration is your pH. The negative log of Ka is something called the pKa, which, by the way, negative log, for those that don't know, is stuffing this number, which could be 1 times 10 to the negative, let's say, 5, into an exponent. In this case, the negative log, I chose a nice number, would be 5. We're stuffing this entire number into a positive exponent. And to go back, we would do 10 to the negative x, 10 to the negative 5 to go back. Now, base 10 logs. So we've got pKa. Now, we're going to convert all these numbers into base 10 logs. Now, I'm going to put a plus here. The reason why is because when you multiply exponents, you're really adding them. Since now these are all exponents, base 10. So now, negative log is the inverse. So I do a negative log, that's 1 over something, so this gets flipped around. So this becomes positive, the log of F negative, the conjugate base, over HF. And this is the Henderson-Hasselbalch equation. It is beautiful, and the reason why it's beautiful is I can solve for the pH as long as I have the Ka, which I convert to a pKa. And look, as long as I have the concentration of the conjugate base, and I have the concentration of the what? Conjugate acid. I know the ratio. Now what's really beautiful about this is I didn't have to do this equilibrium problem here. Watch. Okay, the Ka is 7.2 times 10 to the negative 4. So the pKa, what was that? My short-term memory is gone. 7.2 times 10 to the negative 4. Let's convert that to a pKa by doing a negative log. This gives me 3.14. All right. Plus the log of what? Well, my F negative concentration was what? In molarity. Was 0.15. And my concentration of my acid, I believe, was 0.10. Just make sure no one's screaming at me, and I am correct. Now, let's solve for it. 15.15, I should say, divided by 0.10, probably have to do that, I get 1.5. So this expression right here is 1.5. Let's find a log of 1.5. Log of 1.5 is equal to, this whole expression, 0.176. Not much. So we start at 3.14, and we add a little bit to this pKa, and this plus 3.14 is 3.31, which is our pH. another way to do it. I think a lot easier, but I want you to understand what it really means. How come we only added a little bit? Why? Why was that only a little bit? Because this ratio wasn't that great from each other. 0.15 over 10 isn't that big of a difference. They were very similar. Remember, we made the buffer? We had what? 0.006 and 0.004. They're not the same, but they're similar. But look at this for a second. There's a little more what? Conjugate base. And isn't bases higher in pH? So this little higher base drove this pH a little bit. Not a lot because it's a buffer. Don't forget. Now, just stay with me for a second. What if the conjugate base had the same concentration as a conjugate acid? What if we created a buffer where they were at exactly the same concentration, or in this case, same moles? Well, then you'd have something that would cancel out, wouldn't we? And, oops, sorry. And this something that would cancel out, right here, sorry, this would go to 1, and the log of 1 is 0. So if this was the same number, you made the perfect buffer where you had equal numbers of conjugate base and acid. This would go to 1. The log of 1 would be what? 0. And look at this. The pH would equal the pKa. That is very important. Now you say, well, I don't know if I quite understand that. Well, watch me for a second and I'll finish this off. If we do a titration curve, we plot pH, okay, over volume. And let's say we're adding a strong base. Let's plot this titration, where we're going to add, not that titration, where we're going to add a strong base to HF. Now it's a weak acid, so it doesn't start out as low as a strong acid, but here's what's going to happen. You're going to see something like this. Now, what are we looking at? Well, this right here is something called the endpoint. At the endpoint of a titration curve, this is where all of the hydroxide has equaled all the protons. Now you may say, Mr. Grodsky, we didn't do that. In this titration, we didn't drive all the what? Acid away, did we? No, we didn't. We drove part of it. So if we were to drive it completely what? To its endpoint, it's the endpoint that we did last year where we looked at phenolphthalein turning what? Slightly pink. We're getting in this area. All right? So we didn't get here. So somewhere we're above this point. Now wait a minute. Why is the pH leveling off in this area? It's because we've created a what? A buffer. A buffer prevents the pH from changing. And where do you think the maximum buffer position is? The maximum ability to buffer is when this value equals this value, which means we have the same ability to buffer acids as we do bases. And that buffer position, guys, will be right here, the max buffering position, where you have equal amounts of conjugate acid and conjugate base. I'm sorry, conjugate base is up here, conjugate acid is right here. Maximum buffering position. You have equal amounts. And if you have equal amounts, this will go to 0 and the pH equals the pKa. My friends in chemistry, at this position, you can measure the pH, and whatever that pH is, that is the pKa. And to find the Ka, all you have to do is do 10 to the negative x, and you will get your Ka of your acid. Now, we're almost done. How can I find this max buffering position? Well, once I find the endpoint, this position where the hydroxides equal the H plus in our titration, let's pretend I'm a princess and this volume right here is 100 milliliters. 100 milliliters would mean at this volume of base that we added to the HF, don't lose sight, this is HF being titrated by the hydroxide. At 100 milliliters, I've completely annihilated all the HF. HF is no longer. All you have is F negative. So 100% at this point right here, 100% F negative. So what do you think this position is? And you're going to find something very interesting. This will be 50 milliliters. How much of each do we have to have of the conjugate base and conjugate acid to give me a 1-to-1 relationship? If there's half as much conjugate what? Base to acid, aren't I at the 50% mark here? There'd be 50% F negative. And here would be what? 100%, I'm sorry, HF, right? Here is 50% HF. And here it'd be what at this point here? 0% HF. It's all gone. It's annihilated. So you'll find the max buffering position to always be half the distance in terms of volume of the endpoint or equivalence point. So we're going to see that tomorrow. So we see the curve, we find the endpoint, or we'll find the max buffering position, and that's the halfway titrated. Now, my friends in chemistry, getting back to the problem, this problem wasn't halfway titrated, was it? We were a little what? We were a little further along. We're like right here. Why is it only up a little bit? Because this ratio is here. But if I keep adding more what? Base, my pH rises significantly. So we can measure the pH at about the buffer position using this beautiful Henderson-Hasselbalch equation. Okay? You needed to understand that before the titrations. Thanks.